Hello, welcome to Magnetism 2. In this session we're going to look at force on a conductor. This is the principle of creating mechanical motion or movement using electromagnets. To start with, we need to look at conductors and how they behave when a current is passed through the conductor. What I've sketched here is a battery, not a battery, with a simple circuit, and here we have a conductor. I'm just going to write a conductor. It's a short circuit basically, but it's just a piece of wire. The idea of this sketch is we're going to push some current through this conductor. Okay, when the current flows, what happens is a magnetic field will rotate or appear around the conductor, okay, through its entire length. So what that means basically is obviously the longer the conductor, the more the magnetic field there will be. So length of the conductor has quite a lot to do with the strength. The strength of the magnet. So this principle here is, the handy thing here is that the moment if we take the circuit off, so in other words, if we remove a link, the magnetic field will disappear. So we can create a magnetic field as and when we want it. Okay, so if I put a switch in there now, there's a switch. When I close the switch there, then a magnetic field will rotate. Now, the important thing to remember for theory is if I do the sections, that's looking down a cable. So the electric current, if I draw a cable there, the current is flowing away from view. So the current I is flowing that way. If I was to have to draw another cable with a dot, then the current I is flowing towards view. So away, towards. Very basic, very well documented all over the internet and in various books. So when you see a symbol which has a plus sign right the way through and a dot, that is referring to the direction of current flow in the conductor. So in our conductor here, if we draw a conductor, there's a cross in there, so it's the back of an arrow that's flying away. So we've got north, south, because when the current flows away from view, a magnetic field appears in a clockwise direction. So think of a screw. When you turn a screw clockwise, it goes away from you. Likewise, when we had a conductor and the current is flowing towards view, then the magnetic field flows in the opposite direction, anti-clockwise. This is very important to remember. So now we've got two conductors side by side. You can see that the magnetic poles are south and the south from our previous lesson, that like poles repel. So what would happen here is the fluxes would say, I don't think so, and if those conductors were free in air, they would move, they would force themselves apart because you've got a south and a south. Okay, so remember, cross identifies the current flowing away, which means the magnetic flux will be going in a clockwise direction. That's known as the corkscrew rule. When you turn a corkscrew clockwise, it goes away from you into the cork, and obviously in the opposite direction, looking at it from the other side. So in our last lesson, we looked at a permanent magnet, and we said that with a north pole and south pole, the lines of flux would flow from north to south, and depending on the area of the magnets and the amount of flux, you would get a flux density B, Tesla, from north to south. Okay, that's always going to be there. So with a permanent magnet, that magnetic flux will always be there. So what would happen then if we were to put a conductor at 90 degrees to the magnets? So there's our 90 degrees there. Yeah. So looking down, we've got our North Pole, we've got our South Pole, and right in the middle we've got a current carrying conductor, so the current is flowing away from view, it's going I. What would happen is you would get the magnetic field from the conductor, which I'm going to draw in blue. So that as soon as we switch a current on, as the current flows, a magnetic field rotates around that conductor, but that interferes with the permanent magnet field and it interacts. And what happens is the North Pole of the conductor repels with the field, so this is known as the field winding from north to south, and as a result the conductor will move downwards in a downward force. Okay? If we turn the current off in the centre, then nothing will happen. It will just stay there. But the moment we turn a current on, just to repeat, a magnetic field appears around the conductor, okay, and that interacts with the field winding between north and south, and as a result that conductor is pushed downwards. So what we have here then is the force of the conductor, so the force in which that's going to be pulled down. Force F is measured in newtons after Sir Isaac Newton. F depends on how strong the field, so the magnetic flux density, how long the conductor is, so going back to our beginning, so that length there, so the longer that is, yeah, and last but not least, the amount of current I that's flowing in that conductor. So if we increase the strength of the flux density and or the length of the conductor that's in there and the amount of current flowing in there in the conductor itself, we will increase the force. So B is magnetic flux density, which we looked at in the previous lesson. Remember, that's measured in Teslas. L is the length of the conductor. And that is obviously the SI unit of length is the metre. And I is the current flowing in the conductor. Now the direction of force is determined by using Fleming's left-hand rule. I'm going to save that for another lesson. Okay, but basically if we were to change the direction of the magnetic field, B, so if we swap the magnets round, so north to south, that would change the force would go the opposite direction. Or if we were to change the current flow in the conductor, that would also change the direction of force, but not both. If we change the magnetic field, so north to south, swap those round and change the current flow, the force would remain in the same direction. So this fundamental basic principle is what we use in electrical engineering for motors and solenoids, central locking on motor vehicles, electronic door locks. We are effectively creating a force basically by putting an electric current down a conductor and having two magnetic fields interact. So this forms the basis of basically motors and actuators. Okay, so let's look at an example. A conductor has a length of 25 centimeters and is placed at right angles within a magnetic field. Having a magnetic flux density of 2 Tesla, calculate the force on the conductor when a current of 2.5 amps is reached. So again, F equals BLI, or F equals BIL, some people say. So collect your terms. B is 2 Tesla, L is 0.25 meters. I know it's in centimeters, but be careful. 1, 2, change that. And the current level is 2.5 amperes. Okay, so F is going to be 2 times 2.5 times 0.25. Put that into the calculator, and we get an answer of, very small, but we get 1.25 newtons. Not a great deal, really. So how would we increase that? What we would do is we would increase the strength of the magnetic field, so we would probably put some bigger magnets in there, or we could reduce the resistance of the cable, which would increase the current flow. The only problem with that is if we increase the current in the conductor, it's going to get warmer. The other thing we could do is we could increase the length, but I think realistically in this example it would be probably easier to put some stronger magnets in there, so increase the strength of the magnetic flux. But this also leads on to a motor theory, because obviously the stronger the magnetic field, the more force will be placed on the rotor. So in other words, the more the RPM. And likewise with a solenoid, a door lock. So if you wanted an actual door lock solenoid, then if you increase again the strength of the magnetic field, or you put more turns of wire in there, increase the length, then you're going to increase the force. So just a quick recap then. Basically what we've said is that the direction of current flow in a conductor affects the direction of the magnetic field around the conductor. So if the current flows away, the magnetic field flows in a clockwise direction, hence via the cross. If we were to have a permanent magnet arrangement between north and south, 2 magnets apart, you would get lines of flux, or flux density between the 2 magnets. If we then place a conductor in the middle of the field, so let's call that the field winding there, or the field flux between the 2 poles. If we then place a conductor in the centre and we switch a current through that conductor on, a magnetic field flows around the conductor, which then causes a repulsion between the field and then thus pushes the conductor in the direction shown. If we reverse the direction of the current, so if we were to draw that, so we had north, south, and the current went that way, then the force would be upwards, like so. Okay. Likewise, if we were to change the direction of the magnetic fields, so if we were to say north, south, then what would happen is the force would be changed again. So as long as we change one but not both, we can change the direction of the force on the conductor. So this is a principle really of how solenoids work. It's very basic, but it's a question in most level 2 engineering exams where you will get F equals BLI. In the next lesson, we're going to look at induction, so how we can create a current in a conductor by moving it through a magnetic field, so the generator principle. So this is the motor principle. In the next lesson, we'll look at the generator principle. Hope you found this easy to watch. Thank you for watching. Please put any comments if you need any assistance. Okay, bye for now.